So section 5.3, Sum and Difference Identities, starting on page 121 of your notes packet. Let's start with the sum and difference equations for cosine. So each of these equations is going to be slightly different, but notice that there are some patterns that you can recognize. So starting with cosine of u plus v. So this is the sum of cosine equals cosine of u times cosine of v minus sine of u times sine of v. Now the difference equation for cosine, which is cosine of u minus v, equals cosine of u times cosine of v plus sine of u times sine of v. So when you had the sum, it is equivalent to a difference, and the difference is equivalent to a sum. Those are for cosine. All right, now let's look at the two equations for sine. For the sum, sine of u plus v equals sine of u times cosine of v plus cosine of u times sine of v. And the difference of sine of u minus v, it is equivalent to sine of u times cosine of v minus cosine of u times sine of v. So for cosine, we start with the product of cosine of u and cosine of v, but our sign switches from sum to a difference, right? For sine, the two signs, the addition stays the same, but our first product is sine of u and cosine of v. All right, let's see how we use these. So in example 1, we want to write each of the following expressions as the sine or cosine of an angle. So we want to see if we can condense these down into a single trigonometric expression. So if we're looking at the first part, sine of 22 degrees times cosine of 13 degrees plus cosine of 22 degrees times sine of 13 degrees. The first thing I notice is that I have two terms. They're added together, and each term consists of a sine and a cosine. So that makes me think we're probably going to use the sum of a sine. So sine and cosine in the same term is related to the sine of a sum or difference, and then we have a sum here, and for sine, the signs stayed the same. So we have sine of 22 degrees plus 13 degrees, which equals sine of 35 degrees. All right, you'll do the same thing for the next two problems. Remember to think back to the original equations. In this last example, those are x's, not multiplication symbols. On the next page, looking at example 2, we want to use a sum or difference identity to find an exact value. Notice sine of 15 degrees is not something that we know from the unit circle, so we could rewrite this as sine of 45 degrees minus 30 degrees. Now 45 degrees and 30 degrees are both on the unit circle, so those are values that we know. From our previous definition, we know that sine of a difference gives us sine of 45 degrees times cosine of 30 degrees minus cosine of 45 degrees times sine of 30 degrees. Recall that sine of 45 degrees is the square root of 2 over 2. Cosine of 30 degrees is the square root of 3 over 2 minus cosine of 45 degrees is the square root of 2 over 2. And sine of 30 degrees is 1/2. So now we can compute the square root of 2 times the square root of 3 is the square root of 6, divided by 2 times 2 is 4, minus Square root of 2 times 1 is the square root of 2 divided by 4, which gives us the square root of 6 minus the square root of 2 divided by 4. These are not like radicals, so I cannot simplify that further. So our final answer is the square root of 6 minus the square root of 2 all over 4. Similarly, use the definition of cosine of a sum or difference to find out what two angles will give you pi over 12, and then use this process to find the exact value. All right, now for example 3, we want to match each graph with a pair of the following equations. So we're going to need to look at the graphs on the next page, and then use your knowledge of identities and transformations and not a graphing utility. So no calculators, don't use your computer. Try to use just the things that we've already talked about in this chapter. So I'm going to pull up a picture of the graphs from the next page and kind of scoot over these equations here. Okay, and I'll do the first two. So looking at part A, we have a graph y equals cosine of 3 minus 2 times x. I'm going to go ahead and factor this so that it's in the form that we looked at it in the previous sections. So that's cosine of negative 2 times x minus 3/2. So now we can see that our b value is negative 2 and our h value is 3/2. So what does that mean? It means that our graph of cosine, remember, goes through the maximum at the y-axis, has been compressed by a factor of negative 2. So we're looking at one of these graphs that's been compressed. So that's probably either 33 or 34. And then we also have an h value, or a phase shift, of 3/2. So this doesn't look like it's enough to be a shift or a phase shift of 3/2, but this here, 1.5, is about half of pi. So sure, that it looks like a phase shift of 3/2. So for part A, our answer is 34. All right. Now this answer, 34, will come up again somewhere. So each of these graphs corresponds to two different equations here. All right, let's look at part B. We have sine of x times cosine of 1 plus cosine of x times sine of 1. I look at this double term expression here, and I know that this is a sum of sines. So sine of x plus 1. So again, I have no change in amplitude. My amplitude is 1. No change in horizontal stretch. Just a phase shift here, h equals negative 1. So if there is no value for b, then I'm probably looking at 31 and 32. And then I have a phase shift of negative 1 from sine. So sine usually goes through the origin and is increasing. But now we're going to shift it negative 1. So it doesn't look like 32, but here it could be 31. So the answer for part B is 31. All right, using your knowledge from the previous sections, go ahead and complete parts C through H. And remember, each of these graphs is used twice. All right, and on the next page underneath those graphs, example 4. Use the sum or difference identities and not a graphing utility to solve the equation exactly. So looking at the first problem here, I recognize sine of 2x times cosine of x equals cosine of 2x times sine of x. Looks like a sine equation. So I'm going to subtract cosine of 2x times sine of x from both sides. Sine of 2x times cosine of x minus cosine of 2x times sine of x equals 0. Now I can recognize it as sine of a difference. So I'm saying sine of 2x minus x equals 0. Simplifying the argument, sine of x is 0. And then using the unit circle, we can say sine of x is 0 when our angle when x equals 0 and pi, but also further rotations, so x equals 0 plus 2 pi k and pi plus 2 pi k. All right, for the next one, you'll use a similar technique using the identities, using the sum and difference identities that we already talked about to solve that equation. All right, the last example, example 5, and we're looking to express the function as a sinusoid in the form of y equals a times sine of bx plus c. The first example is y equals 3 times sine of x plus 4 times cosine of x. Now, how do we get from this form to this form? We're going to need to use something that uses a sum, and the way to think of it is first to look at what we want. So we want it in this sinusoidal form, and we can actually expand this sinusoidal form using the sign of a sum. So a times sine of bx cosine of c plus cosine of bx times sine of c. Now we want something times sine of x plus something times cosine of x. So notice here I have a sine of x and a cosine of x, and it has a b, but we'll figure that out in a second. So I'm going to distribute the a, but write the sine of x at the end and the cosine of x at the end of their terms. So a cosine of c times sine of bx plus a sine of c times cosine of bx. So now I have something that's a very similar form to what I'm looking for, except that my coefficient here, 3 equals a times cosine of c, and my second coefficient, the coefficient of the cosine term, here is 4, so I want that to equal a times sine of c. And then here I don't have a coefficient of the x, so I want my b to be 1. So now I need to solve for a and for c. And I see that I have a cosine term and a sine term. If I want to solve for one of those variables, maybe I can use the Pythagorean identity. So let's try if I say a cosine of c squared plus a sine of c squared equals 3 squared plus 4 squared. Calculating that square, I have a squared cosine squared c plus a squared sine squared of c equals 9 plus 16. So factoring out that a squared is cosine squared c plus sine squared of c equals 25. So now we have that Pythagorean identity. A squared times 1 equals 25. So a squared is 25, and a is plus or minus 5, taking the square root of both sides. And we can just say, I want to let a be 5. So either of those could work. We're selecting the positive one because it will be easier to work with. So then coming back up here, I can say 3 equals 5 times cosine of c. 4 equals 5 times sine of c. These should give us the same c value, so you can choose which one you'd like to calculate. Let's choose cosine. So dividing both sides by 5, cosine of c equals 3/5. Now we don't know what value of c will give us a cosine value of 3/5, so we can use the inverse function. And we can say that c is equal to cosine inverse of 3/5. It would also be equal to sine inverse of 4/5 if we had calculated it that way. All right, now we have a value for a value for b, and a value for c, so we can substitute it into our equation. Y equals 5 sine of 1 times x plus cosine inverse of 3/5. All right. Similarly, you'll use the same process for the next example, and then reflect on what you learned from this lesson and write a summary in the box below.